Welcome to the Deep Dive, where we take a stack of information and unearth the most important insights for you. Today, we're embarking on a pretty fascinating journey into the world of data engineering. Our mission is simple: give you a clear, conversational, and practical overview of everything a smart non-specialist or maybe a junior data engineer really needs to know. Think of it as your essential guide to understanding how data moves, lives, and, well, breathes in the digital world.
Exactly. We'll explore core concepts, essential technologies, and the crucial role data engineers play. And we'll do it without getting bogged down in, heavy math or super dense theory. The goal is really to provide those aha moments, leaving you well-informed and feeling ready to tackle your next data challenge. Hashtag tag data and databases foundations.
Okay, let's unpack this then. Chapter 1, data and databases, the absolute foundations. We hear data constantly, but what exactly is it? It feels like anything sometimes.
It pretty much is. Data is simply information or facts. Could be your name, age, a picture, a video, that social media post you just liked. Any information, really. It comes in tons of forms: images, video, files, plain text. Even just ones and zeros at its most basic level.
Got it. So it's the raw stuff. And where does all this raw stuff live?
In a database. Think of it like a container or maybe a really systematic library collection for data. It's electronically stored, and its whole purpose is to make data easy to access, modify, protect, and analyze. Honestly, most websites and apps you use daily, Google, Instagram, Facebook, they all run on databases. They couldn't function without them.
Okay, so the database is the container. But it doesn't just manage itself, right? There's got to be software involved.
That's exactly where a database management system, or DBMS, comes in. The DBMS is the software that lets you actually do things with the database, create it, define its structure, manipulate the data inside. It's the interface. It lets users store, process, analyze data easily. It handles all the core operations.
Like a create, read, update, delete, CRUD.
It's exactly CRUD. Plus, it handles security, like user access permissions, ensures data consistency so things don't get messed up, and manages backups. Crucial stuff.
And the way we've done this has changed a lot over time, hasn't it? The evolution.
Oh, absolutely. It's been quite a ride. Started super simply with flat files, like CSVs, way back in the 1960s. Then we had hierarchical and network databases, but they kind of struggled with complex relationships between data. The really big leap, the one that became the backbone for ages, was relational databases.
Right, SQL databases.
Yep. But then the web exploded, right?
Oh.
Suddenly we had massive amounts of data, especially semi-structured stuff like emails or unstructured like images and video. And that's when NoSQL databases emerged, specifically designed to handle these new, more diverse data demands at scale. So the key takeaway here: data is information in all sorts of formats stored in databases. And those databases are managed by DBMS to make everything accessible, modifiable, and protected.
Makes sense. And a common pitfall to avoid.
Oh, definitely storing all your important data in just simple spreadsheets or flat files. It seems easy at first, but it quickly leads to redundancy, inconsistency, and honestly just major headaches as your data starts to grow. Hashtag schemas and architecture.
Okay, so we have data in a managed database, but how do we organize it so it's not just a jumbled mess? That brings us to our next section: schemas and architecture, giving data structure and shape.
Exactly. A schema is essentially the blueprint for your database. Think of it like architectural plans for a house. It defines the structure, things like tables, views, the fields within tables, and the relationships between them. Without a schema, you're just lost in a jumble of data. It's like trying to find a specific document in a totally disorganized, unlabeled filing cabinet. Chaos.
And I understand there are different ideas about when you apply that structure.
That's a key distinction. We talk about schema-on-write versus schema-on-read. Schema-on-write is the traditional approach used by relational databases. It enforces structure before any data is stored. Every single piece of data has to conform to that predefined format, that blueprint.
Okay, so it's strict up front.
Right. Schema-on-read, on the other hand, stores data more in its raw, sometimes jumbled state. The structure is applied only when you actually query or read the data. That's pretty common in, say, data lakes or for unstructured data. Because it offers more flexibility up front, you figure out the structure later.
Interesting trade-off. Now, beyond the schema, how are the databases themselves set up? The overall system design, that's architecture, right?
Yep. Database architectures describe how the database, the application using it, and the end user all interact. The simplest form is one-tier architecture. Everything database, application logic, user interface is on a single server.
Like maybe an old Microsoft Access file on your home PC.
Exactly like that. Then things get a bit more distributed. A two-tier architecture separates the client application from the database server. But really, the most common and advantageous setup today is the three-tier architecture. Here you have three distinct layers: the database itself, an intermediate server layer that handles the business logic, and then the application or presentation layer that users actually interact with.
Okay, 3 layers. Sounds potentially more complex, but what's the big win? Why is that the standard now? Security, scale.
Both, and more. It's a huge win for security because that middle server layer acts like a gatekeeper or a firewall. It vets the request before they even hit the database, which protects it.
Ah, okay.
And for scalability, it's great because you can scale each tier database, server, application independently. If your application needs more power, you scale that tier without touching the database directly.
That makes sense. Better resource allocation.
Right. Plus, it improves reliability. If one tier has an issue, it's less likely to bring down the whole system, unlike that single server setup. And honestly, it allowed for faster development because different teams can work on different tiers simultaneously.
Okay, good stuff. And one last distinction in this area, OLTP versus OLRP workloads. What's that about?
Right. Important difference. OLTP stands for Online Transactional Processing. Think day-to-day operations. Recording an e-commerce order, a bank transfer, updating customer info. It deals with live, real-time, very detailed individual records. Lots of small reads and writes.
Okay, transactional. Got it.
Then there's OLA, which is Online Analytical Processing. This is all about analyzing huge amounts of historical data, often summarized data to find insights, trends, patterns. Think building reports, business intelligence dashboards, fewer but much more complex queries over large data sets.
So different jobs require different database focuses.
Exactly. Your system needs to handle both, often, but the database design might be optimized differently for each. So, the takeaway. A schema is your data blueprint, applied either on write for consistency or on read for flexibility. And three-tier architecture is generally the winner for modern apps, offering better security, scalability, and reliability for both OLTP and OLIP tasks.
And the common pitfall here.
Designing a database without a clear schema or a proper architectural plan from the start, it almost inevitably leads to what people call data swamps, messy, unusable data, and painfully slow analytics down the road. We saw a lot of this in the early big data craze with things like Hadoop, #ACD and normalization.
All right, moving on. When we're talking about things like, money changing hands, financial transactions, or even just critical business operations, reliability is absolutely paramount. So our next deep dive is into two concepts that guarantee that reliability: ACD and normalization.
Absolutely essential concepts, especially when you need trust in your data systems. AC properties are a must-have for reliable database transactions. ACD is an acronym standing for atomicity, consistency, isolation, and durability. These four properties work together to ensure that transactions are processed reliably, even if the system crashes or something else goes wrong halfway through.
Okay, ACD. Let's break those down. Can you give us some plain English examples? Atomicity first.
Sure. Atomicity means a transaction is an all-or-nothing deal. It's indivisible. Think about transferring $100 from Alice's account to Bob's. Atomicity ensures that either $100 is subtracted from Alice and $100 is added to Bob, or if anything fails, maybe the system crashes after subtracting from Alice, but before adding to Bob, the entire transaction rolls back. It's as if it never happened. No money lost, no money created out of thin air.
Okay, all or nothing. Got it. Consistency.
Consistency means that any transaction must follow all the predefined rules and constraints of the database, leaving the data in a valid, good state. For instance, if your bank has a rule that account balances cannot go below zero, the database's consistency rules will prevent a withdrawal transaction that would violate this rule. The transaction gets canceled to keep the data valid.
So it enforces the rules. Isolation. This one sounds tricky with lots of users.
Isolation is about how concurrent transactions, multiple transactions happening at the same time, interact with each other. Even if many transactions are running simultaneously, isolation aims to make it seem like each transaction has the database all to itself. It prevents weird interactions, like preventing one transaction from reading data that another transaction hasn't finished committing yet. That's a dirty read. Or preventing a transaction from seeing different results if it reads the same data twice, a non-repeatable read. The highest level, called serializable, essentially makes transactions run one after another, ensuring the strongest consistency, but it can impact performance.
Okay, keeping simultaneous operations from tripping over each other. And finally, durability.
Durability means that once a transaction has been successfully committed, it's permanent. It will survive system crashes, power outages, whatever. Even if the database server crashes milliseconds after confirming your transaction, the change is safe. This is usually achieved through techniques like writing to transaction logs before confirming or replicating data across multiple machines.
Okay, so ACD gives us that transactional guarantee. Super important. How does normalization fit into this picture of reliability and good data?
Normalization is more about the structure of your database tables, specifically aiming to reduce redundancy, storing the same piece of information multiple times, and protect data integrity. If your data starts contradicting itself, like maybe you have the same customer listed with two different dates of birth in different places, that's often a sign of poor database design, not just bad data entry. Normalization helps prevent these kinds of issues, called anomalies. Well-normalized tables are generally easier to understand, easier to modify later, and inherently protect against these inconsistencies.
And I remember hearing about different normal forms, like levels of normalization, almost like safety ratings.
That's a great analogy. Yes, there are different normal forms, representing increasing levels of structural integrity. We usually talk about first normal form, 1NF, second normal form, 2NF, and third normal form, 3NF. There's also Boyce-Codd normal form, BCNF, which is a slightly stricter version of 3NF, and even fourth 4NF and fifth 5NF for really complex, rarer scenarios.
Okay, so what do the main ones fix? Like 1NF.
1NF sets the basic rules. No repeating groups within a single row, like storing multiple phone numbers in one text field or having item 1, item 2, item 3 columns. Each column must hold atomic values, and every table needs a primary key. It forces you to break repeating groups into separate rows or tables.
Okay, basic tidiness, 2NF.
2NF builds on 1NF and deals with tables that have composite primary keys, keys made of multiple columns. It says that every non-key attribute must depend on the entire primary key, not just part of it. If it only depends on part, you split it out into a new table to avoid update and deletion anomalies.
Anomalies like losing data accidentally.
Exactly, or having to update the same info in multiple places.
And 3NF, BCNF, the usual target.
Right. 3NF and BCNF tightens this, builds on 2NF. It says that no non-key attribute should depend on another non-key attribute. This is called a transitive dependency. A common mnemonic is that attributes must depend on the key, the whole key, and nothing but the key. If you have, say, player-id, team-id, and team name in one table, team name depends on team-id, a non-key attribute, not directly on player-id. So you'd split team-id and team name into a separate teams table. This prevents inconsistencies. For most practical purposes, reaching 3NF or BCNF is considered a well-normalized design. 4NF and 5NF handle more obscure dependency types.
Got it. So normalization is key for clean, reliable structure.
Absolutely. The takeaway here, ACID properties, atomicity, consistency, isolation, durability, guarantee your transactions are reliable. Database normalization, especially up to 3NF BCNF, guarantees your data structure is efficient, avoids redundancy, and prevents integrity problems.
And the common pitfall if you ignore normalization.
You end up with data integrity failures. Your data starts contradicting itself, becomes untrustworthy, and you suffer from those insertion, update, or deletion anomalies that make managing the data a nightmare. Hashtag relational databases, SQL.
We've mentioned them a few times, but let's really hone in now on arguably the most dominant database paradigm for decades, relational databases and their language, SQL.
Yeah, it's hard to overstate the impact. The Relational Database Management System, the RDBMS, it's truly one of the most successful ideas in computing history. And SQL structured query language, even though it dates back to the 1970s, it still forms the absolute backbone of so much of the modern data world, even big data. You've got giants like Oracle dominating the enterprise space, and then open source powerhouses like MySQL and PostgreSQL driving huge platforms. Think YouTube, Facebook, they heavily rely on relational principles.
Okay, so what is a relational database at its core? How does SQL actually work with it?
Fundamentally, a relational database organizes data into tables. You could picture them like spreadsheets, really. Each table has columns, which define the attributes or the type of data, like name, age, city, and it has rows, where each row represents an individual record or data point, like one specific customer. And crucially, each row usually has a unique identifier called a primary key. Think of it as a unique ID number for that record.
Okay, tables, rows, columns, primary keys. Pretty straightforward. But the relational part implies connections, right? How do tables link together?
Exactly. That's done using foreign keys. A foreign key is a column, or set of columns, in one table that refers back to the primary key of another table. So if you have a players table and a teams table, the players table might have a teamid column that acts as a foreign key, linking each player to their specific team record in the team's table via the team's primary key. This ability to define and enforce relationships across multiple tables is really where SQL gets its power.
So SQL isn't just for pulling out a single row or updating a single value. It's about combining data.
Oh, absolutely. SQL is used for the basic CR-ROOT operations, reading, creating, updating, deleting data. But its real strength lies in its ability to join data together from multiple tables based on these defined relationships. You can use the select statement to choose which columns you want, the where clause to filter rows based on conditions, and crucially, the join clause to combine data from, say, the players and teams tables to get a player's name alongside their team's name. This makes relational databases incredibly powerful for maintaining data integrity, ensuring relationships are valid, and they are typically the ideal choice for OLTP, online transactional processing workloads we mentioned earlier, like handling e-commerce orders or financial transactions where consistency is key.
Makes sense. But what happens when you scale up like billions of records? How do these traditional relational databases handle that kind of load?
That's historically been a challenge. Traditionally, relational databases scale vertically,
Meaning,
meaning you make the single server they run on more powerful, add more CPU, more RAM, faster storage. You buy a bigger box, basically. But obviously, there are physical and cost limits to how big you can make a single machine. You can't scale vertically forever.
so what about horizontal scaling? Adding more machines instead of just bigger ones?
Right. For massive scale, relational databases have developed patterns for horizontal scaling. The main ones are replication, partitioning, and sharding. Replication involves making copies of the database across multiple servers. Often you have one primary write server and several read replicas. This helps distribute the load for read-heavy applications and provides high availability if one server fails.
Okay, copies for reads and backup. Partitioning.
Partitioning means dividing a single large table into smaller, more manageable pieces, or partitions, maybe based on date ranges or geographic regions. But often these partitions still live on the same database server. Sharding takes partitioning a step further. It actually distributes these partitions across multiple different database servers called shards. Each shard holds a subset of the data. This allows for true horizontal scaling. If you need more capacity, you just add more shard servers to the cluster.
Sharding sounds like the answer for huge scale then, but I imagine it's not simple.
Not at all. It introduces significant complexity. While sharding offers immense scalability and fault tolerance by distributing the load, managing it can be tough, especially dealing with cross-shard queries that need to access data living on multiple different shards. These can become very complex to route and potentially slow to execute because you have to coordinate across machines.
So there are trade-offs.
Definitely. Technologies like PlanetScale for MySQL and YugaDB for PostgreSQL are newer platforms aiming to make this kind of horizontal scaling feel more seamless, sometimes using underlying tech like Vites to manage the sharding complexity for you. So the takeaway on relational databases. They organize structured data into tables with strong relationships, queried using SQL, great for integrity and OLTP. Scaling traditionally involves vertical upgrades, but for web scale, horizontal patterns like replication and especially sharding are used, though sharding adds significant operational complexity.
And the common pitfall.
Thinking you can easily scale a traditional relational database horizontally for massive web scale applications without careful planning. If you don't properly implement and manage techniques like sharding, you can get serious performance bottlenecks or create an overly complex system. Tag NoSQL families and when to use.
Okay, we've covered the relational world thoroughly, but what about that other universe you mentioned, NoSQL, for when data isn't neat rows and columns, or when you need massive scale perhaps more easily?
Yeah, exactly. NoSQL, which really means not only SQL, represents a pretty significant departure from the strict structures and sometimes the strict consistency guarantees of relational databases. They generally prioritize things like flexible schemas, easier to change data structures on the fly, and horizontal scalability, meaning they're often designed from the ground up to run across many machines easily.
But there's usually a trade-off, right?
Often, yes. A common trade-off, especially in distributed NoSQL systems, is moving from strict ACID consistency to what's called eventual consistency. We'll touch on that. A core idea behind many NoSQL models is that every item in the database stands on its own. You try to avoid those complex, sometimes costly joins between tables that are central to SQL.
Interesting. So it's a different philosophy. What are the main types, the families, of NoSQL databases? And crucially, when would you actually use each one?
Right, there are several distinct families, each suited for different tasks. Let's run through the main ones. First, key value stores. These are the simplest. Think of a giant dictionary. You store data as a unique key mapped to a value. That value could be anything: text, an image, a JSON object. They're incredibly fast, often running in memory.
Use cases.
Perfect for caching frequently accessed data to speed up applications, think Redis or KDB. Also great for managing user session information for websites or maybe leaderboards in games.
Pitfall.
Querying is limited. You can basically only look things up by their exact key. Searching based on the value is usually difficult or impossible.
Okay, next type.
Document databases. These store data in semi-structured documents, most commonly using JSON or similar formats like BSON or XML. The beauty is, each document can have its own structure. They don't all need to follow the exact same schema.
Makes sense. Use cases.
Great for things like product catalogs where products have varying attributes, content management systems, or generally any application where the data structure might evolve frequently. MongoDB is a very popular example. Fauna is another interesting one.
Pitfall there.
Can lead to data duplication if the same piece of info needs to be in multiple documents, meaning updates have to happen in many places. And joins across documents are often not natively supported or efficient, making complex relational queries harder.
Right. What's next?
Wide column stores. These are designed for handling absolutely massive data sets, often structured data, distributed across potentially hundreds or thousands of servers. They are typically optimized for very heavy write workloads and high availability. Think Cassandra or HBase.
Use cases.
Best suited for write-heavy applications, storing time series data at enormous scale, application logging, or collecting data from millions of IoT sensors, inspired by Google's Big Table and Amazon's Dynamo papers.
Downside.
They can be quite complex to set up and manage. Schema design requires careful thought, often overkill, unless you really need that massive scale and write performance.
Okay. Getting more specialized now. Graph databases.
Yeah, these focus specifically on the relationships between data points. Instead of tables, you think in terms of nodes, which are like records or entities, and relationships or edges, which are the connections between nodes and can have properties and direction.
Use cases sound relationship heavy.
Exactly. Perfect for analyzing complex networks like social graphs, who's friends with whom, fraud detection, connecting seemingly unrelated transactions, recommendation engines, finding connections between users and items. Neo4j, EdgeDB, SerialDB, memgraph are examples here.
Potential pitfall.
Query languages are often specific to the graph database, like Cypher for Neo4j, so there's a learning curve. And you need to be careful not to infer misleading connections if the model isn't designed well.
Makes sense. And vector databases. These seem newer.
They are relatively new and booming, especially with AI. Vector databases are optimized for storing and searching vector embeddings.
Embeddings.
Embedding is essentially a long list of numbers that represents complex, unstructured data like a paragraph of text, an image, or an audio clip in a mathematical way. The key is that similar items will have mathematically close vectors.
Ah, so you can find similar things easily?
Precisely. Use cases include semantic search, finding text based on meaning, not just keywords, image or audio similarity search, building better recommendation engines, and critically, giving large language models, LLMs, long-term memory and context by finding relevant information. That's Retrieval Augmented Generation, or RAG. Milvus and Pinecone are big names here.
Pitfall.
Definitely overkill if your main need isn't similarity search on unstructured data. A traditional database might be perfectly fine for many tasks.
Got it. Two more quick ones. Time series databases.
Optimized specifically for data points that are time-stamped measurements or events tracked over time. Think server metrics, application performance monitoring, network data, IoT sensor readings again, but maybe with specific time-based query needs. InfluxDB and Prometheus are common examples.
Pitfall.
Not good for general-purpose data. Really designed for that time series pattern.
And finally, search engines as databases.
Yeah, sometimes tools like Elasticsearch, Milasearch, or Algolia are used like specialized databases. They aren't usually your primary data store, but you often duplicate data into them specifically to enable powerful, fast, full-text search features within your application, allowing fine-tuning of relevance and ranking. It's duplicated data, so you have the overhead of keeping it in sync with your primary store. Now, underpinning many of these distributed NoSQL systems is that concept I mentioned, CAP intuition. The CAP theorem basically states that in a distributed system, one running on multiple machines that might have network issues between them, you could only strongly guarantee 2 out of 3 properties. Consistency, all nodes see the exact same data at the exact same time. Availability, every request gets a response, even if it's slightly stale data. Or partition tolerance, the system keeps working even if parts of the network fail. Because network partitions do happen, distributed systems usually have to choose between prioritizing consistency, C, or availability, A. Many NoSQL databases opt for availability and partition tolerance, AP, which leads to that eventual consistency data will eventually become consistent across all nodes. But there might be brief moments where different nodes see slightly different versions.
Fascinating trade-off, driven by the realities of distributed systems.
Precisely. So the big takeaway for NoSQL, it offers flexibility in schemas and excels at horizontal scaling. Different families: key value, document, wide column, graph, vector, time series, search are optimized for specific use cases. And be aware of the consistency trade-offs, often leaning towards eventual consistency, availability over strict consistency, in distributed setups, guided by the CAP theorem.
And the overarching pitfall.
Using a NoSQL database when your core requirement is strict A/C compliance and you need complex, multi-table joins, like a traditional relational database provides. Trying to force NoSQL into that mold can lead to data inconsistencies or require you to build really complex logic in your application to handle things the database doesn't guarantee. Choose the right tool for the job. ### big data engines.
Okay, we've talked databases, SQL and NoSQL, but what happens when the sheer volume of data becomes astronomical? We're talking terabytes, petabytes. This is where big data engines come into play, right?
Absolutely. In the early 2000s, the internet, social media, sensors, they just started generating data at a scale never seen before. Traditional databases and processing methods simply couldn't keep up. This gave rise to the term big data, which refers to these extremely large, often complex, and rapidly growing data sets. And this demanded new tools.
And the first big breakthrough was Hadoop, wasn't it?
It really was. Around 2006, inspired by some internal papers from Google about their MapReduce framework and distributed file system, engineers at Yahoo developed Hadoop. It was a game changer because it pioneered affordable, distributed processing. The idea was to use clusters of relatively cheap commodity hardware, just standard servers, working together to store and process massive amounts of any kind of data, structured or unstructured.
How did it work? What were the core parts?
The Hadoop basically had two main components initially, later joined by a third. First, HDFS, the Hadoop Distributed File System. This is the storage layer. It takes huge files, breaks them into large blocks like 128 millibs by default, and spreads these blocks across many machines, data nodes, in the cluster. Crucially, it replicates these blocks, usually 3 times by default, across different machines for fault tolerance. If one machine dies, the data is still safe on others.
Okay, distributed, redundant storage, and the processing.
That was MapReduce. This is the original processing framework for Hadoop. It works in 2 phases, map and reduce. The map phase takes the input data, processes it in parallel across the different data nodes where the blocks reside. The reduce phase then takes the intermediate results from all the mappers and aggregates them to produce the final output.
Can you give an example?
The classic example is counting word occurrences in a massive collection of documents. The map tasks on each node would count words in their local data blocks. The reduce task would then sum up the counts for each word from all the mappers to get the final totals. MapReduce is designed for batch processing, running large jobs over large data sets, and it was very disk-heavy. It wrote intermediate results to disk between the map and reduce phases.
And the third component you mentioned.
This came a bit later. YARN, which stands for Yet Another Resource Negotiator. As Hadoop clusters started running more than just MapReduce jobs, YARN was introduced to manage the cluster resources, CPU, RAM, network, more efficiently and allow different types of applications to run concurrently on the same hardware.
So Hadoop was revolutionary for handling big data, but I feel like I hear less about it now. Did it have limitations?
It did. Its biggest limitation was performance, largely due to that reliance on disk for intermediate MapReduce results. Disk I/O is slow compared to memory. Also, its primary model was batch processing. You'd submit a big job, wait for it to finish, then maybe submit another. It wasn't great for more interactive queries or real-time processing needs that started emerging.
Which created an opening for something faster.
Exactly. And that's where Apache Spark swooped in.
Ah, Spark. I hear that name constantly.
You do, because it largely addressed Hadoop's limitations and has become a dominant force in big data processing. Developed at UC Berkeley around 2009, Spark's main innovation, its killer feature, is in-memory speed. Instead of writing intermediate data to disk like MapReduce, Spark tries to keep as much data as possible in RAM across the cluster during processing.
And RAM is way faster than disk.
Orders of magnitude faster. This makes Spark significantly faster than Hadoop MapReduce for many tasks, potentially up to 100 times faster for certain iterative algorithms common in machine learning.
Wow. How does Spark manage data in memory?
Its core abstraction was originally the RDD, or Resilient Distributed Dataset. Think of it as an immutable, distributed collection of objects that can be processed in parallel. More commonly used now, though, are higher-level abstractions built on RDDs, especially data frames and datasets. Data frames organize data into named columns, much like a table in a relational database or a pandas data frame in Python. They are easier to work with and allow Spark to perform significant optimizations under the hood. You can even run SQL-like queries directly on data frames using Spark SQL.
And Spark isn't just faster batch processing, right? It does more.
Correct. Spark is a unified engine. Spark SQL lets you run SQL queries. Spark Streaming, and its successor, Structured Streaming, allows for processing of live, real-time data streams, not just batches. And MLlib is Spark's built-in library for scalable machine learning.
So this really highlights the difference between batch and streaming processing.
Precisely. Batch processing deals with large volumes of static data, collected over a period, processed all at once. Think generating end-of-day reports. Streaming processing deals with continuous, unbounded flows of data, processing events as they arrive, often within milliseconds or seconds. Think real-time fraud detection, monitoring live sensor data, or updating website analytics instantly. Hadoop, especially early Hadoop with MapReduce, was primarily batch-oriented and disk-heavy. Spark excels at both batch and streaming, with a huge advantage in speed due to its in-memory processing capabilities, making it ideal for interactive analysis and real-time applications. So the key takeaway: Hadoop pioneered distributed big data processing with HDFS and batch-focused MapReduce yarn. Apache Spark emerged as a much faster, more versatile engine leveraging in-memory computation for both batch and real-time streaming workloads, becoming a cornerstone of modern big data stacks.
And the common pitfall in this area.
Sticking with older, disk-heavy batch processing engines like traditional Hadoop MapReduce, when your actual business need is for real-time or near-real-time analytics. Trying to get fast insights out of a slow batch system leads to significant delays in decisions based on outdated information.
Okay, so we have these powerful engines like Spark to process massive amounts of data. But once it's processed, or even before, where does all this data get stored specifically for analysis and business intelligence? That brings us to our next chapter, comparing data warehouses, data lakes, and the newer concept of a data lakehouse.
Right. Think about analytic storage, like organizing a large commercial kitchen. Raw ingredients arrive, they need to be stored. Some need prepping and organizing before they can be used in specific recipes. Data architecture often follows a similar flow.
Okay, I like the kitchen analogy. So what's the data warehouse in this kitchen?
The data warehouse, sometimes called an enterprise data warehouse or EDW, is like the meticulously organized pantry and walk-in freezer. It's a central repository of integrated, structured, and clean business data that has been specifically modeled and optimized for analytical querying and reporting, that OLP workload we talked about. Data loaded into a warehouse is typically curated, governed, validated. It's often considered the single source of truth for key business metrics. Think historical sales data, customer information, all structured for easy reporting.
So it's the clean, ready-to-use ingredients, prepped and labeled. What about a data lake then?
The data lake is more like the loading dock and maybe some basic bulk storage shelves at the back of the kitchen. It's designed to cheaply and quickly capture all types of data in its raw, native format, structured, semi-structured, unstructured. Think raw server logs, social media feeds, images, videos, maybe copies of transactional database tables. The idea is flexibility and cost-effectiveness. Capture everything now, figure exactly how you'll use it later. Don't throw potentially valuable data away just because you don't have an immediate use or structure for it.
That sounds great, cheap, flexible storage. But I've definitely heard the term data swamp associated with data leaks. What's the risk?
That's the big one. A data lake without proper management and governance can easily turn into a data swamp. This happens when it gets filled with lots of duplicate data, undocumented data, poor quality data, or data nobody understands or trusts anymore. It becomes hard to find anything useful. If the data becomes stale, unreliable, or unusable, it loses all its potential value. It's like having a loading dock piled high with rotting ingredients because nothing was ever properly sorted, labeled, or processed. Data lakes also typically struggle with query performance for the kind of complex analytical queries that data warehouses are optimized for, because the data is often raw and not structured for analysis.
Okay, so warehouse is structured and clean, but maybe less flexible and potentially more expensive upfront to set up. Lake is cheap and flexible, but risks becoming a swamp.
Right.
Is there a middle ground, something that tries to combine the benefits?
That's precisely the motivation behind the data lakehouse concept, which has gained a lot of traction recently. The idea is to take the best of both worlds. The low-cost, flexible storage of a data lake, often built on top of cloud object storage like Amazon S3 or Google Cloud Storage, but add data management features, metadata layers, and query engine capabilities more typically found in data warehouses. Technologies like Delta Lake, Apache Iceberg, and Apache Hudi provide transactional capabilities like ACID, which lakes traditionally lacked, schema enforcement, and performance optimizations directly on top of the raw data files in the lake. This allows you to store diverse data types cheaply but still manage them effectively, enforce quality, and run high-performance SQL queries for both traditional BI and more advanced machine learning workloads directly on the lake data.
Interesting. So it's bringing warehouse-like structure and performance to the lake environment. How does data typically flow into these systems? I hear ETL and ELT mentioned.
Good question. That describes the sequence of operations. ETL stands for extract, transform, load. This is the traditional data warehousing approach. You extract data from source systems, like your CRM, ERP databases. Then you transform it, clean it, aggregate it, reshape it according to the warehouse's predefined schema before you finally load it into the data warehouse. The transformation happens in a separate staging area.
So the data landing in the warehouse is already clean and structured?
Right. ELT, on the other hand, stands for extract, load, transform. This pattern is more common with data lakes and lakehouses. You extract data from sources, then you load it directly into the data lake, often in its raw format. The transformation happens later within the lake or lakehouse environment using powerful processing engines like Spark.
Why the shift towards ELT?
Flexibility, mainly. Loading raw data first means you preserve the original detail, which might be useful later for different types of analysis, like machine learning, that weren't anticipated initially. It also leverages the power and scalability of modern query engines within the lakehouse to do the transformations, rather than requiring a separate transformation engine.
Makes sense. So quick recap on governance and cost.
Data warehouses generally offer stronger governance and data quality enforcement due to their curated nature, but they can be more expensive and less flexible for unstructured data. Data lakes are cheap and flexible, but carry that significant risk of becoming ungoverned swamps. Lakehouses aim to strike a balance, cost-effective storage like a lake, but with added layers for governance, quality, and performance, making diverse data types usable for analytics.
Any examples of popular platforms in this space?
Sure. Cloud platforms like Google BigQuery, Snowflake, Amazon Redshift, and Databricks, which heavily promotes the lakehouse concept, are all major players offering powerful data warehousing and/or lakehouse capabilities as managed services. So the key takeaway: data warehouses provide curated, structured data optimized for traditional OLA PBI. Data lakes offer cheap, flexible storage for raw data, but risk becoming swamps without governance. Data lakehouses aim to combine lake flexibility and cost with warehouse management and performance, often using an ELT approach.
And the common pitfall seems pretty clear.
Letting your data lake descend into chaos. Failing to implement proper data governance, metadata management, and quality controls basically turns your cheap storage into a useless data swamp, negating the whole point. #tag integration and pipelines.
Right. Data needs to be stored, it needs to be processed, but it also needs to move. It doesn't just magically appear where we need it. So our next chapter is all about integration and pipelines, how we build the systems to transport and transform data between different sources and destinations.
Exactly. This is really the bread and butter of a lot of data engineering work. A data pipeline is essentially a system that automates the movement and processing of data. Think of it like a water pipe system. It takes data from one or more sources, like databases, applications, external services, potentially performs some transformations along the way, cleaning, enriching, aggregating, and then loads it into a target location, like a data warehouse, a data lake, or another application.
Building and managing these pipelines is a core job for data engineers then.
Absolutely. Making sure data flows reliably, efficiently, and correctly from where it's generated to where it needs to be consumed.
Okay, so how do different applications or systems even talk to each other to exchange this data in the first place?
APIs are fundamental here. An API, or application programming interface, is basically a set of rules and protocols that allows different software systems to communicate and exchange data with each other.
What are the common types of APIs we encounter?
The most dominant standard for web APIs today is REST, which stands for Representational State Transfer. REST APIs typically use standard HTTP methods you've probably seen: get, under, retrieve, data, post to create data, put to update data, delete to remove data. They operate on resources, like users or orders, and are generally stateless, meaning the server doesn't need to remember anything about the client between requests. This makes them very scalable and easier to build and maintain. Responses are very often formatted in JSON.
JSON.
Now, JSON, JavaScript Object Notation, has become the de facto standard data format for web APIs, especially REST APIs. It's text-based, lightweight, human-readable, and easy for machines to parse. Data is represented using key-value pairs, nested objects using curly braces, and arrays using square brackets. It's much simpler and less verbose than older formats like XML, which makes data transfer and processing faster.
Okay, so REST APIs using JSON are common for request-response interactions. But what about data that's constantly flowing, like real-time updates?
Great point. For that, we move beyond simple request-response APIs into the realm of event streaming. And the dominant technology here is Apache Kafka.
Kafka seems to be everywhere in modern data architectures.
It really is. Kafka acts as a distributed, persistent, high-throughput log system. Think of it as a central nervous system for data in an organization. It allows different applications to publish streams of events, like website clicks, orders placed, sensor readings, and other applications to subscribe to these streams and react to them in real time. It's a key enabler for decoupling systems and moving towards microservice architectures.
How does Kafka organize this flow of events?
Data in Kafka is organized into topics. A topic is like a category or feed name for a specific type of event stream, Shiji, orders, user signups. Topics are then broken down into one or more partitions. Partitioning allows Kafka to distribute the data for a single topic across multiple servers called brokers in the cluster. This enables parallel processing and high scalability. Messages within a partition are ordered.
And how do applications read from these topics?
Applications read data by forming consumer groups. Multiple instances of an application can belong to the same consumer group, and Kafka ensures that each message within a topic partition is delivered to only one consumer instance within that group. This allows you to scale out your processing by simply adding more consumer instances to the group.
Kafka sounds powerful, but maybe complex to integrate with everything.
It can be, but the ecosystem helps. Kafka Connect is a framework that provides pre-built connectors to easily stream data from various source systems, like databases maybe using change data capture or CDC to get real-time changes, into Kafka, and from Kafka to various sync systems like data lakes, warehouses, or search indexes, without writing a lot of custom integration code. And as data formats evolve, the schema registry plays a crucial role in data governance. It stores and enforces the schemas, the structure of the messages being published to Kafka topics, ensuring that producers and consumers agree on the data format, preventing errors when schemas change.
So Kafka is the highway for real-time data. What about processing that data while it's still streaming?
That's where stream processing engines come in. Tools like Apache Flink or Spark Streaming, which we mentioned earlier, are designed to consume data streams from Kafka or other sources and perform complex computations on the fly. Think filtering events, joining different streams together based on common keys, aggregating data over time windows, like calculating average sensor readings over the last 5 minutes, or detecting patterns in real time. Flink is particularly well regarded for its sophisticated state management and low-latency processing capabilities.
Okay, we have APIs for requests, Kafka for streaming, Flink for stream processing. Putting this all together into a reliable pipeline sounds like a lot of moving parts to manage. How do you schedule these jobs, handle dependencies, monitor failures?
That's exactly the job of orchestration tools. And one of the most popular open-source tools in this space is Apache Airflow. Airflow allows you to define your data pipelines as code, usually Python. You define workflows, schedule them to run automatically, monitor their progress, and handle failures and retries.
How does Airflow represent these workflows?
The core concept in Airflow is the DAG, which stands for Directed Acyclic Graph. A DAG is essentially a blueprint of your workflow. It's a collection of all the individual tasks you want to run, organized in a way that shows their relationships and dependencies. Directed means the tasks run in a specific order, and acyclic means the workflow doesn't have loops. It has a clear start and end.
And the tasks themselves?
Tasks within a DAG are defined using operators. Airflow comes with many pre-built operators, like a bash operator to run a shell command, a Python operator to run Python code, operators to interact with databases, cloud services, etc., and you can create custom ones. Airflow's scheduler monitors your DAGs and triggers task runs when their dependencies are met and the schedule time arrives. For example, run this pipeline daily at 3 a.m. Executors are the components that actually run the tasks. They can run locally on one machine or be distributed across multiple workers using systems like Celery or Kubernetes. Airflow provides a UI to visualize your pipelines, see their status, check logs, and manually trigger runs, which is invaluable for managing complex workflows.
So Airflow brings order to the potential chaos of many interacting jobs.
Precisely. The takeaway for integration: APIs, especially REST with JSON, enable communication between systems. Event streaming platforms like Kafka provide the real-time data backbone, often feeding stream processors like Flink. And orchestration tools like Airflow are essential for scheduling, managing, and monitoring these complex data pipelines.
And the pitfall to avoid.
Trying to manage more than a handful of simple data pipelines using basic tools like cron jobs or scattered scripts, as soon as you have dependencies between jobs, need retries on failure, require monitoring, or need to scale, it becomes an unmanageable headache. You really need a proper orchestration tool like Airflow, #HAG Cloud and DBAS plus CDN.
So much of this infrastructure we're talking about, databases, processing engines, pipelines, where does it actually run these days? Increasingly, it's in the cloud, right?
Overwhelmingly so.
Yeah.
The shift from running servers in your own data center on-premises to using cloud platforms like Amazon Web Services, AWS, Google Cloud Platform, GCP, or Microsoft Azure has been massive over the last decade or so.
And one specific cloud offering that's really relevant to our database discussion is DBAS. What exactly is that?
DBA stands for Database as a Service. It's pretty literal. The cloud provider offers you a database instance as a managed service. Instead of you having to worry about ordering server hardware, installing the operating system like Linux, installing the database software like PostgreSQL or MySQL, configuring it, patching it, setting up backups, the cloud provider handles almost all of that underlying infrastructure management for you.
So you just click a button and get a database.
Almost. You typically specify the database type you want, the size or performance tier you need, and maybe some configuration options through a web console or API call, and the cloud provider provisions and manages a ready-to-use database endpoint for your application to connect to.
Okay, that sounds incredibly convenient. What are the big advantages? What does DBase really buy you?
The primary benefit is a massive reduction in your operational burden. The cloud provider takes responsibility for tasks like hardware provisioning and maintenance, operating system patching, database software patching and upgrades, setting up and managing backups, ensuring high availability, often through automatic failover to standby instances, monitoring the underlying infrastructure, guaranteeing a certain level of uptime via service level agreements, SLAs. You don't need dedicated database administrators, DBAs, just to keep the lights on, handle server crashes, or figure out how to restore data from backups in an emergency.
So it frees up your team to focus on actually using the data, building applications, doing analytics.
Exactly. You offload the undifferentiated heavy lifting of basic database operations to the provider, allowing your team to focus on higher value tasks that are specific to your business. It also often means faster time to market for new projects because getting a database ready takes minutes, not days or weeks.
Seems like a no-brainer. Are there any downsides? Any trade-offs for this convenience?
Yes, there's always a trade-off. The main one is less control. Because the provider is managing the underlying infrastructure and software, you typically lose the fine-grained, root-level access you'd have if you managed it yourself. You can't always tweak every single configuration parameter of the OS or the database engine to optimize it perfectly for your specific, perhaps unusual workload. You might have less visibility into exactly what's happening under the hood, and you're dependent on the provider's schedule for patching and major version upgrades. So you might not be able to squeeze out that last 5% of performance.
Potentially. You might sometimes need to provision a slightly larger or more expensive DBase instance, oversize it, compared to what you could achieve with a perfectly tuned, self-managed setup to get the same performance. However, for most organizations, the TCO, total cost of ownership, often works out favorably for DBAS when you factor in the saved operational overhead, the reduced need for specialized staff, and the built-in high availability and durability features that would be complex and expensive to replicate yourself. Makes sense. Okay, shifting gears slightly, but still in the cloud realm, content delivery networks, or CDNs. How do they fit into the data picture?
CDNs are crucial for delivering content, especially static content, like images, videos, JavaScript files, CSS style sheets, but sometimes dynamic content too, to end users quickly and reliably across the globe. A CDN is essentially a geographically distributed network of proxy servers. They cache copies of your website's content in locations much closer to your users than your origin server might be.
So if my website is hosted in, say, Virginia, but a user accesses it from London, the CDN might serve the images from a server in London instead.
Exactly. This significantly improves latency, reduces delay, because the data travels a much shorter physical distance. This makes websites and applications feel much faster and more responsive for users.
And it's not just about speed, right? They help with reliability, too.
Yes, hugely important. CDNs help absorb traffic spikes. If your site suddenly gets very popular, The distributed nature of the CDN spreads the load across many servers, preventing your single origin server from getting overwhelmed. They also provide a critical layer of protection against DDoS attacks, distributed denial of service. CDNs can often detect and mitigate malicious traffic at their edge servers before it ever reaches your application's origin, helping to keep your service online even under attack. Some newer concepts are even pushing database capabilities closer to the edge, like Cloudflare's D1, which is essentially a SQLite database running on their global CDN network, aiming to serve dynamic data faster, similar to how CDNs serve static content.
Interesting convergence.
Definitely. So the takeaway, DBMS offers managed database services in the cloud, drastically reducing operational overhead for patching, backups, and high availability, though it comes with less granular control. CDNs, meanwhile, are essential for improving website application performance by caching content closer to users, reducing latency, and protecting against traffic spikes and DDoS attacks.
And a potential pitfall.
For DBMS, perhaps not fully understanding the cost implications of different performance tiers or features. For self-managed databases, the big pitfall is definitely underestimating the constant operational effort required. Failing to dedicate resources for regular patching, robust backup testing, and setting up proper high availability can easily lead to major security vulnerabilities, catastrophic data loss, or significant downtime when something inevitably goes wrong. DBMS often prevents these self-inflicted wounds. ## memory and storage basics. Performance intuition.
Okay, we've talked a lot about databases, engines, cloud services, but to really understand why some systems are fast and others are slow, or why some choices are better for certain workloads, we need to get down to the fundamentals. Let's touch on memory and storage basics, building some performance intuition from the hardware level up.
Yeah, this is super important for developing that gut feeling about performance. At the very bottom, every piece of data in a computer, whether it's a movie file, a database record, or line of code, is stored as bits. Binary digits, just zeros and ones. The computer's brain, the CPU, central processing unit, processes millions or billions of these bits every second. The fundamental challenge for computer designers, and consequently for us using these systems, is always balancing three things: storage size, capacity, cost, and speed. How fast we can access the data. You usually can't maximize all three at once.
Makes sense. So how does a computer manage data it needs right now versus data it needs to keep for later? Short-term versus long-term memory.
It's very much like human memory in that sense. Computers have both fast, temporary working memory and slower, persistent long-term storage. Short-term memory is primarily RAM, random access memory, and even faster CPU caches. This is where the computer holds data and program instructions that it's actively working on right now. When you launch an application, the operating system loads parts of it into RAM.
And there are different types of RAM.
Yes. The main type you find in desktops and servers is DRAM, dynamic RAM. Each memory cell uses a tiny transistor and capacitor to store a charge, representing a 1 or 0. It's dynamic because these charges leak away quickly and need to be constantly refreshed thousands of times per second to retain the data. Accessing data from DRAM typically takes around, say, 50–100 nanoseconds. Then, even faster is SRAM, static RAM. This is used for those CPU caches, L1, L2, L3 caches, that sit directly on or very close to the CPU chip. SRAM uses a more complex structure, usually 6 transistors per bit, that doesn't need refreshing. This makes it much faster than DRAM, maybe 110 nanoseconds access time, but it's also much more expensive and takes up more physical space on the chip. That's why you have megabytes of cache versus gigabytes of RAM.
Okay, so cache, SRAM, is fastest. RAM, GRAM, is next fastest. Both are for active work. What about keeping data when the power goes off? Long-term storage.
Right. For data to persist after the power is cut, it needs to be written to long-term storage, which we usually call drives. There are a few main types here too, varying dramatically in speed and cost. Magnetic storage, primarily HDDs, hard disk drives. These store data as magnetic patterns on spinning platters. They offer the lowest cost per gigabyte and high capacity, but they are incredibly slow compared to RAM because you have physical moving parts. The disk has to spin and the read-write head has to move to the right track. Latency is measured in milliseconds, which is tens or hundreds of thousands of times slower than DRAM.
Huge difference. What else?
Optical storage like CDs, DVDs, Blu-ray discs. These also use spinning disks, but store data as tiny pits or flat spots on a reflective surface read by a laser. They're cheap and removable, but generally even slower than HDDs and have lower capacity. Less common for primary data storage now. And the big one today: solid-state drives, SSDs, which includes things like the drives in modern laptops, servers, and USB flash sticks. These use flash memory, a type of non-volatile memory. There are no moving parts. They store bits by trapping electrical charges in floating gate transistors.
And they're much faster than HDDs.
Way faster. Access times are typically in the microseconds range, so hundreds times faster than HDDs, though still significantly slower than RAM. They become the standard for performance-sensitive storage.
Okay, so speed hierarchy is roughly cache, RAM, SSD, HDD, optical. What about durability? How long does this stuff actually last?
That's a really important point, often overlooked. Computer memory and storage are not permanent archives in the way people sometimes think. They degrade. Heat is a major enemy. It can demagnetize hard drives over time. It can degrade the dyes used in optical media. For SSDs, the trapped charges in those floating gates can slowly leak away, causing data loss. This usually takes years, but it happens. SSDs also have another specific weakness: write endurance. The act of writing data actually wears out the insulating layer around those floating gates. Each cell can only be reliably written to a certain number of times before it fails. Modern SSDs have sophisticated wear-leveling algorithms to spread writes out, but they do eventually wear out. Honestly, most current consumer and even enterprise storage media probably have a reliable life expectancy under 10 years, if not actively managed. This is why redundancy, backups, and data migration strategies are absolutely critical for long-term preservation.
Wow, less than 10 years is shorter than I might have guessed. So, tying this back to data systems, how do these hardware choices directly impact performance metrics like throughput and latency?
Well, it's fundamental. Latency, the delay in accessing data, is lowest when data is closest to the CPU and the cache, this RAM. It increases significantly as you move further away. To RAM, then SSDs, then HDDs. Throughput, how much data can be transferred per second, generally follows the same pattern. Highest for cache RAM, lower for SSDs, and lowest for HDDs. Durability persistence is the trade-off. Cache and RAM are volatile. Data disappears instantly when the power goes off. SSDs and HDDs are non-volatile or persistent data stays even without power, at least for a while. So think about an in-memory database or cache like Redis or PDB. They store data primarily in RAM for ultra-low latency and high throughput, handling millions of operations per second. But they aren't typically used as the primary permanent system of record because RAM is expensive and volatile. You still need to persist important data to SSDs or HDDs. The choice of storage directly dictates the performance characteristics of your database or application.
Great explanation. So the takeaway. Hardware choices are critical for performance. SRAM cache is fastest but small expensive. DRAM RAM is fast, volatile working memory. SSDs offer much faster persistent storage than HDDs.
This hierarchy directly impacts system latency and throughput, with a trade-off against volatility and cost. Understanding these basics gives you intuition about why certain data systems perform the way they do.
And the common pitfall.
Underestimating just how massive the performance difference is between memory and disk, even fast SSDs. Trying to build a system that requires extremely low latency or very high transaction rates using primarily disk-based storage, HDDs, or even sometimes relying too heavily on SSDs without sufficient RAM caching will almost certainly lead to performance bottlenecks. Choosing the right storage tier for the workload is critical. #tag data engineer role and skills.
We've covered an incredible amount of ground databases, architectures, big data, pipelines, cloud, hardware. Now let's bring it all together. Who are the people actually building and managing all this? Let's talk about the role of the data engineer and the skills needed to succeed in it.
Right, the unsung heroes in many ways. Data engineering is fundamentally like building and maintaining the engine room or the plumbing system for any company that relies on data, which is pretty much every company today. A data engineer is the person responsible for designing, building, and managing the systems that move, transform, and store massive amounts of data efficiently and reliably. You're often working behind the scenes, taking complex, sometimes messy data from various sources, cleaning it up, structuring it, and making it available on a suitable platform so that others like data analysts, data scientists, or applications can actually use it to do smart things.
So less about the final analysis or building the prediction model, more about making sure the data is there, correct, and accessible for those tasks.
Exactly. You're enabling those downstream uses. You expose the important data and make it usable.
What does a typical day or maybe a typical week look like for a data engineer? What kind of tasks are they doing?
It varies a lot depending on the company and the specific role, but common activities include ingesting data. Setting up processes to pull data from various sources could be APIs from third-party services like Google Analytics or Salesforce, internal SQL databases, streaming sources like Kafka, flat files dropped onto a server, etc. Modeling and transforming data. This is a huge part. Taking that raw ingested data and cleaning it, handling missing values, standardizing formats, structuring it, maybe applying a schema, combining data from different sources, aggregating it, and generally getting it into a format that's useful for analysis or application use. This often involves writing code or using specialized tools, loading data, moving the transformed data into its final destination, which might be a data warehouse like Snowflake or BigQuery, a data lake, a NoSQL database, or maybe feeding it back into an operational system. Monitoring and maintenance, this is critical. Keeping an eye on existing data pipelines to make sure they're running successfully, troubleshooting failures, optimizing performance, ensuring data quality remains high. It's like checking for leaks or blockages in the plumbing. Building and evolving infrastructure. You might also be involved in choosing the right tools, setting up new databases or processing clusters, adding new data sources to existing pipelines, and constantly thinking about how to scale the systems as data volumes inevitably grow.
It sounds like a mix of software engineering, database administration, and system architecture. What are the absolute core skills someone starting out, maybe a junior data engineer, should really focus on mastering?
Yeah, it's definitely a multidisciplinary role. For core skills, I'd highlight these. 1. SQL. Absolutely non-negotiable. It's the lingua franca for interacting with structured data and relational databases, and it's heavily used in data transformation within warehouses and even in engines like SparkSQL. You need to know more than just basic select statements, understand joins thoroughly, window functions, common table expressions, CTEs, maybe some basic query optimization. 2. Python. This has become the dominant programming language for data engineering tasks. It's incredibly versatile. You'll use it for scripting pipelines, connecting to APIs, writing various file formats, CSV, JSON, Parquet, performing complex transformations, often using libraries like Pandas, but less so at massive scale where Spark takes over, automating tasks, and interacting with orchestration tools like Airflow. Strong fundamentals in Python data structures, lists, dictionary sets, and file handling are key. 3. Spark, PySpark. For dealing with truly large data sets, big data, Apache Spark is the industry standard. Learning Spark, especially via its Python API, PySpark, is crucial. You need to understand the basic architecture, driver, executors, how RDDs and especially data frames work, and how to use Spark's APIs for distributed data transformation, aggregation, and joining. If you master PySpark, you're well equipped for almost any big data project. 4. Git. Essential for version control. All your pipeline code, SQL scripts, configurations, it all needs to be stored, versioned, and collaborated on using Git. You need to be comfortable with creating repositories, committing changes, branching, merging, handling pull requests, cloning, and resolving merge conflicts. It's fundamental for team collaboration and deploying code reliably.
Okay, SQL, Python, Spark, Git, what else?
5. Data modeling. Understanding how to structure data effectively is critical. This includes concepts like dimensional modeling, star schemas, Snowflake schemas, commonly used in data warehouses, maybe understanding alternatives like Data Vault, and generally knowing how to design schemas that are efficient, understandable, and meet the analytical needs. 6. Understanding batch versus stream processing. Knowing the difference in the basic principles of building pipelines for both scenarios. 7. Partitioning. This technique is vital for optimizing performance and managing costs when dealing with large data sets in warehouses or lakes. Understanding how to partition data effectively, for example, by date, is a key practical skill. 8. Cloud platform fundamentals. Since almost everything runs in the cloud now, having foundational knowledge of at least one major cloud provider, AWS, Azure, or GCP, is essential. Understanding their core storage services like S3, GCS, ADLS, compute options, database services like RDS, Cloud SQL, Azure SQL, and basic networking and security concepts. 9. CI/CD basics. Understanding continuous integration and continuous deployment principles, how code gets tested automatically and deployed smoothly from development to production environments. This is becoming increasingly important for data pipelines too.
That's a solid list. Any practical tips for someone trying to break into the field or get hired as a data engineer?
One really strong tip: build a portfolio and showcase it on GitHub. Theoretical knowledge is good, but employers want to see that you can actually build things. Create 1 or 2 solid personal projects that demonstrate your skills. Maybe build a pipeline that ingests data from a public API, processes it with Python and Spark, stores it in a database or data lake. You can often use free tiers of cloud services. Maybe models it using SQL and documents it well with a clear readme file in your GitHub repository. A clean, well-documented GitHub profile showing practical application of SQL, Python, Spark, and maybe a cloud data platform like Databricks or Snowflake speaks volumes to potential employers.
Great advice. Focus on demonstrating practical skills.
Absolutely. So the takeaway: data engineers are the essential builders and maintainers of the data infrastructure. They manage the entire lifecycle of data ingestion, transformation, storage, monitoring. The role requires a strong blend of technical skills, primarily SQL, Python, Spark, PySpark, Git, along with data modeling concepts, cloud platform knowledge, and an understanding of both batch and stream processing paradigms.
And the common pitfall for aspiring data engineers.
Focusing solely on the coding aspects and underestimating the importance of supporting skills like Git for collaboration, clear documentation, or fundamental data modeling principles. You can write clever code, but if the data model is confusing or the pipeline isn't version controlled and documented, it's not a robust or maintainable system, which is crucial in professional environment. #check choosing the right tool. Decision checklist.
Wow, okay. We have covered an enormous amount of ground today. We've gone from basic data definitions all the way to specific tools like Spark, Kafka, Airflow, different NoSQL types, cloud services. It's a lot to take in. How does anyone, whether they're a junior engineer or just trying to understand the landscape, possibly choose the right tool or combination of tools for their specific project or problem? This feels like where the rubber really meets the road.
It absolutely is, and you hit the nail on the head. There is no single best database or best data processing tool. The right choice is always context dependent. It depends entirely on your specific use case, your requirements, your constraints. Trying to use one tool for everything is almost always a mistake. But we can provide a simple framework, a kind of checklist, to help guide that decision-making process.
Okay, a decision framework. That sounds useful. What are the key questions to ask?
Here are the main factors I'd consider roughly in order. 1. Workload type. What is the primary job this system needs to do? Is it mostly OLTP, handling lots of small, real-time reads and writes like user transactions in an application? Or is it primarily OLP, running complex analytical queries over large volumes of historical data for reporting and insights? Some systems need to support both, often called HD hybrid transactional analytical processing, which presents its own challenges. 2. Data shape or structure. What does your data look like? Is it highly structured, fitting neatly into tabular rows and columns, ideal for relational databases? Is it more like semi-structured documents with varying fields, suggesting a document database like MongoDB? Is the key insight hidden in the relationships between entities, pointing towards a graph database? Are you dealing with vector embeddings for a similarity search, requiring a vector database? Or is it fundamentally time series data, sequences of measurements over time? 3. Scale and latency requirements. How much data are you dealing with now, and how much do you expect in the future? Gigabytes, terabytes, petabytes, and what are your performance needs? Do you need millisecond latency for real-time responses in an application? Or are seconds, minutes, or even hours acceptable for batch analytical jobs? This heavily influences choices between in-memory versus disk, or different scaling architectures. 4. Consistency needs. How critical is it that every read sees the absolute latest committed write? Do you need strict ACID compliance, like for financial systems? Or is eventual consistency acceptable, where there might be a small delay before all replicas reflect the latest update, common in highly available distributed systems like social media feeds? This is the CAP theorem trade-off we discussed. 5. Operational budget and management. How much are you willing or able to spend on infrastructure, software licenses, if any, and ongoing operational maintenance? Do you have the team and expertise to manage the system yourself, or would you prefer a fully managed service, DBMS, where the cloud provider handles the operational burden even if it costs a bit more or offers less control? 6. Team skills and ecosystem. What technologies does your team already know and feel comfortable with? Introducing a completely new technology stack has a learning curve and integration cost. How mature is the ecosystem around the tool? Libraries, community support, documentation. Sometimes choosing a slightly less perfect but familiar tool is better than picking the ideal but obscure one.
That's a really practical checklist. Workload, data shape, scale latency, consistency, budget ops, team skills. Can you maybe walk through a couple of common scenarios and suggest what a reasonable starter stack might look like based on that framework?
Sure, absolutely. Let's take a few examples. Scenario 1. A typical OLTP application, like an e-commerce backend managing users, products, orders. Workload. OLTP, many small reads, writes, high concurrency. Data shape, mostly tabular structured. Relationships are important. Users place orders for products. Scale latency, needs low latency, sub-second responses. Scale might grow, needs good handling of concurrent users. Consistency, needs strong consistency. ACID is important for orders, inventory. Decision, a traditional relational database is usually the best fit here. Starter stack, PostgreSQL or MySQL, perhaps as a managed DBMS offering like AWS, RDS, or Google Cloud SQL. To handle reload as it grows, add read replicas. If schema flexibility becomes a major pain point later, maybe consider a document DB like MongoDB for certain parts, but start relational. Scenario 2. business intelligence and analytics platform, analyzing sales trends, user behavior, workload. OLE, complex queries over large historical data. Data shape, often starts tabular but might need to incorporate semi-structured data too. Scale latency, needs to handle large volumes, terabytes plus.
Query latency of seconds to minutes is often acceptable for reports. Consistency. Eventual consistency might be okay for loading data, but queries need consistency within the analytical snapshot. Decision. A cloud data warehouse or lakehouse using an ELT approach is ideal. Starter stack. Extract data from sources, load it, maybe raw, into cloud storage like S3 GCS. Use a cloud data warehouse like Snowflake, BigQuery, or Databricks to transform and query the data using SQL. Add a transformation tool like DBT, data build tool, to manage the SQL transformation logic effectively. Connect a BI tool like Tableau, Power BI, Looker for visualization. Scenario 3. Real-time monitoring or fraud detection, processing IoT sensor data or transaction streams instantly. Workload. Streaming processing, low latency analysis of continuous data. Data shape, often semi-structured events, JSON. Time is critical, may involve joining streams or looking up reference data. Scale latency, needs to handle high throughput streams with low latency, milliseconds to seconds. Consistency, needs timely processing, maybe eventual consistency is okay for some downstream analytics, but the detection logic needs recent data. Decision. A streaming architecture is required. Starter stack. Use Apache Kafka as the central event streaming bus to ingest the real-time data. Use a stream processing engine like Apache Flink or Spark Streaming to process, analyze, join, or aggregate the data on the fly. Feed the results into a downstream system, maybe another Kafka topic, a fast NoSQL store for quick lookups like Redis, or potentially land process data into a lakehouse like Databricks Delta Lake for near real-time analytics.
Those examples really help illustrate how the framework leads to different technology choices.
Exactly. It forces you to think through the requirements first, rather than just jumping to a familiar or trendy tool. So, the critical takeaway here. Choosing the right data tool is not about finding the single best one. It requires using a decision framework. You need to carefully consider your workload type, OLTP OLAST streaming, data shape, scale and latency needs, consistency requirements, operational capacity, and your team's skills. This often leads to using a combination of different specialized tools for different parts of your overall data architecture.
And the final common pitfall.
Trying to force a one-size-fits-all database or platform onto every single data problem within your organization. Using your main transactional database for heavy analytics will kill its performance. Using a key value store when you need complex relational queries will lead to application complexity. Using a data warehouse for real-time streaming ingestion might not work well. You end up with suboptimal performance, increased complexity, or higher costs because the tool just isn't suited for that specific job. Hashtag outro.
So after that comprehensive journey, what does this all really mean for you, our listener?
Well, we've really covered the waterfront of data engineering today, haven't we? We started with the fundamentals. What data actually is, how databases and DBMSs manage it. We looked at the importance of schemas and architectures for structure. We dove into the crucial A-C-D properties that ensure transactional reliability and the normalization techniques that keep data structures clean and consistent.
Yeah, then we navigated the different worlds of databases, the structured, reliable realm of relational databases and SQL, contrasting that with the diverse and flexible families of NoSQL databases, exploring when and why you'd use each type, from key-value stores to graph and vector databases.
We powered through the evolution of big data engines. Understanding why Hadoop emerged and how Apache Spark then revolutionized processing with its in-memory speed for both batch and streaming data.
We explored the different strategies for analytics storage, the curated data warehouse, the raw data lake, and the hybrid data lakehouse, and how data gets into them via ETL or ELT.
We then charted the course of data in motion through integration and pipelines, looking at APIs like REST, the critical role of event streaming with Kafka, real-time processing with tools like Flink, and managing it all with orchestrators like Airflow.
We touched on the impact of the cloud, the convenience and trade-offs of database as a service, and the importance of CDNs for delivering content quickly.
We even peeked under the hood at memory and storage basics to build that performance intuition, connecting hardware choices to latency and throughput.
And finally, we outlined the vital role and the broad skill set required of a data engineer and provided a framework to help you make informed decisions when choosing the right tools for your own data challenges.
Phew, it's a lot. But hopefully, this deep dive reveals just how much engineering work goes on behind the scenes. That digital world you interact with, constantly streaming shows, online shopping, using apps, it all relies on the often invisible talent and Yes, sweat of data engineers, making sure the data flows correctly and efficiently.
It really underscores how foundational this field is.
Absolutely. And looking ahead, the future of technology, especially artificial intelligence, is completely dependent on access to high-quality, well-processed, reliable data. That just highlights how indispensable data engineering will continue to be.
We really hope this deep dive has served as a valuable shortcut, helping you connect the dots and maybe sparking some of those aha moments we aimed for. And to leave you with something to think about. As data technologies continue to evolve so rapidly, and as AI becomes more deeply integrated into everything, how do you think the very definition of data itself might continue to expand and transform in the next 5 or 10 years? What new kinds of information will we need to engineer pipelines for?
That's a great question to ponder. For more insights into the cutting edge of data, AI, and related technologies, you can subscribe to Algorythmos AI wherever you get your podcasts. We'll have another deep dive for you soon. Thank you so much for joining us today.